To introduce our next section, let's look back at what we've done so far. We've described motion with words, we've described motion with graphs, and now I'd like to transition from graphs into our third section of describing motion with equations. To do so, let's revisit the moving man. We have a situation here where the moving man leans against the tree at a position of -10 meters for 1.50 seconds before hearing a disturbance in his house. He begins moving at 2.00 meters per second, increasing his speed up to 6.00 meters per second over a time of 5 seconds in order to reach the house and investigate. We're asking what was the man's acceleration and what distance did the moving man cover between the tree and the house. From our first section, I can find the acceleration of the man. I know that acceleration is change in velocity over change in time. So, if he started, separating that is going to be v final minus v initial over my change in time. Well, his final speed is 6.0 meters per second. His initial speed was 2 meters per second, and it took 5 seconds. So I would like to get a speed, or an acceleration, of 4 over 5, which is 0.800 with 3 sig figs. Meters per second, or 0.800 meters per second squared. My next question is asking what distance did the moving man cover between the tree and the house. So we're asking for our displacement from the tree to the house. The equation I have for displacement relates velocity and time. That comes from rearranging the definition of velocity. However, this is a constant velocity equation. It only works if I'm moving at a constant speed, which we've already clarified is not happening. So I cannot use this red equation to find my distance. We don't have the tools in our toolbox yet. So let's use graphs to expand our toolbox. I'm going to draw my velocity graph to do so. Velocity measured in meters per second, and time measured in seconds. So let's go through the situation again. The moving man is leaning against the tree for 1.5 seconds. Leaning against the tree involves not moving. So from 0 to 1, 2, 3, 4, 5, 6. 0 to 1.5, he is not moving. 0 speed. He then hears a disturbance in his house and begins moving at 2 meters per second. 1, 2, 3, 4, 5, 6. So he immediately jumps up to 2 meters per second. And from there, he takes an additional 5 seconds to reach the house. So from 1.5 to 6.5. And at 6.5 seconds, he reaches his max speed of 6 meters per second. Since we know it, he increases his speed uniformly. Nice straight line. Okay, we'll only have straight lines in our velocity graphs. That's him speeding up. Alright, so that's the information that we have. And I can confirm this green work by looking at the slope of my graph. Alright, I get my final velocity minus my initial velocity to get delta V and delta T, which was 5 seconds. Alright, so that's using the equation we already had and using the relationship between position, velocity, and acceleration. We're taking the slope of this graph to solve for acceleration. However, I want to now figure out what was the displacement that my moving man covered. All right, so to do so, I'm going to introduce this method by finding my change in velocity using an acceleration graph. I know this might seem simple, but it's going to help us better understand this process to get displacement. So if I were to graph my acceleration, get rid of this work in the middle. Proper units on my scale. Again, the moving man was stationary at the beginning for the first 1.5 seconds, and then it jumps to this constant 0.800 for 5 more seconds, up to 6.5 seconds. So how are we going to use this? Well, from this green equation, I can rearrange this to solve for my change in velocity. So the acceleration times time is going to be my change in velocity. And if I'm looking for this area under the curve, which we found in our velocity time homework earlier, and I take the area under the curve of this velocity graph, it's bounded by the value of the acceleration, it's bounded by my time axis, or the acceleration equals 0 axis, and then my time conditions. When was he accelerating? From 1.5 seconds to 6.5 seconds. So it's going to be my delta t is my boundary, and then my acceleration value is my boundary. And that creates an area under the curve of a rectangle. How do I find the area of a rectangle? Length times width. Well, the length of this is delta t. That's my 5 seconds. And the vertical width of this is my acceleration, 0.8. So that's going to give me my change in velocity. It's the exact same equation, just rearranged. And when I take that 5 seconds times 0.800, I get a change in velocity of plus 4 meters per second. And I can take this up here now. If I know I started at 2, because they told me in the problem, my change in velocity will be plus 4, and I wind up with 6 meters per second after those 5 seconds that I used in the equation. Alright, so we're just confirming knowledge using this area under the curve method, so that we can now use it from our velocity time graph to come up and solve for displacement. Alright, so what is the area under this curve? Here is my velocity curve. It's bounded by my time, velocity equals 0 axis, and the end of my time. And as we saw in the last homework, this is a funky shape. It is a trapezoid. You can easily split these up into much more simpler shapes of a rectangle and a triangle. Alright, so what is this rectangle? This rectangle is going to be, again, my 2 meters per second. It's going to actually be my, I'll replace it with variables at the very end. It's going to be 2 meters per second as the height of that rectangle, times the length of that rectangle, which is our 5 seconds. Okay, so that's 2 times 5. And then this triangle, right? We know the area for triangles is 1/2 base times height. So 1/2, what's the base of this? It is my time of 5 seconds. What is the height of this? Is my change in velocity from 2 to 6 of 4. Alright, so I said the variables as I wrote them, but let's rewrite this as well. This is my initial velocity of 2 seconds times my time, okay, or delta time for this section, plus 1/2 times my time times that change in velocity. This change in velocity for the height of the triangle. And we've already defined the change in velocity here. So I can substitute this up and write this as the acceleration times delta t. So the expression that we're going to get is that our displacement is our initial velocity times time plus 1/2 times can combine, and I get acceleration times time squared. And this is going to be the expression that we can use to solve for displacement while accelerating. This would be the expression to use when you're not accelerating. All right, that was our constant velocity. And if you notice, if you're not accelerating, look what you get. The expression for constant velocity. So this displacement equation will always be useful for any motion we look at, relating position, initial velocity, acceleration, and time. And so plugging this into our situation, with the numbers I have here, 2 times 5 is 10, plus our triangle of 1/2 times 5 times 4, 5 times 4 is 20, half of that is 10 again, so I get a displacement of positive 20 meters, which is the distance from the tree to the house in our problem. So with our graphs, we have now found another equation here. We have confirmed the equation that we knew from the definition of acceleration. I'm actually going to split this up so that we can get our first equation for displacement. Our second equation, I'm going to split up delta V to be V final minus V initial and solve for V final equals V initial plus our acceleration times time on this side. In each of these equations, they are super useful because the first equation does not use final velocity. The second equation does not use displacement. So if you're given any 3 of these 4 variables, you can solve for it. You don't need final velocity. Right? So there's 5 the big 5 variables. Displacement, initial velocity, final velocity, acceleration, and time. 4 of them will be in the equation, 1 of them will be missing. And it can be very helpful sometimes to find an equation that does not involve time. So if we go through some fun algebra, solve for time here, plug it in there, it gets a little complicated, and we wind up with your final velocity squared equals your initial velocity squared plus 2 times the acceleration times your displacement. And that's going to involve not using time. Alright, so a nice visual there of our kinematic equations that we're going to be using now for the next few weeks. Feel free to ask questions, and best of luck with your problem sets.